is the first video lecture about static single assignment, which is a type of intermediate code representation. This is a very brief intro to SSA, and we'll cover in more detail in future video lectures how we can actually generate SSA from non-SSA form intermediate code. So let's look at a control flow graph. So when you have a for loop, in this case, you have the initialization, you have the check whether the condition is true or not to execute the for loop, you have the post condition, and you have the body of the for loop over here. Each of those cases are each represented by these basic blocks. All of these basic blocks here are linked together using goto statements to create the control flow graph. So as you enter, you first initialize it. After initializing, you check whether the condition is true. You execute the loop. At the end of it, you calculate the post condition, which goes in here, and then it goes back all the way and checks again whether the condition is true. So that's how the for loop works, and if the condition is false, it exits out of the for loop. So this is what a sort of standard control flow graph looks like. Let's take a look at it in a little bit more detail in 3-address code, which is talked about in more depth in the video lecture on intermediate code representation. So we cover 3-address code in that. But the idea here is taking the same for loop, but we now have it in 3-address code. So we have to compute the Boolean expression. We check whether the Boolean is false. If it is false, we go to L1, which means we exit the loop. If it isn't false, what we do is compute the different aspects of the for loop, and then in the end we add 1 to I, which is the post condition in the for loop, and then we go to L0. So it goes back to L0 over here, and it does the check again, and if it's true, it does the body of, so this part over here is the body of the for loop. So you can see it graphically over here. It comes in, it does an initialization over here in this, and then it does the check for the condition, and then does the body of the for loop. In this case, let's focus on the variable I. I is first defined up in that first basic block over there. And then it is, in this case, it's unambiguous. There's only one definition for I, one place where I is defined. It reaches this location. By reaches, I mean used. Essentially, I is used in this line of code here. As you can see, checking whether I is less than T1. It also calls a function with the argument the value is I. So again, it's used over here on this line. And then finally, it's both used. So it is used here, but it also is killed in the sense it's redefined. So these are some of the terms people use when talking about data flow, but they often use definition, reaches, and kill. The value is killed or redefined in this case. So what we want to do is analyze where the variables are used separately from where the variables were redefined essentially. So as you can see, we're using the same variable I both on the right hand side and the left hand side. So the idea behind static single assignment form is to keep these two separate. So when you use it, it should use a variable that was defined once. And then if you want to redefine the variable, you can't change the value of an existing variable. Essentially, every variable here is a constant or cannot be rewritten. If you want to rewrite something or use something to create a value that previously you were doing a redefinition, you have to actually create a new variable. And this simplifies the defined use chains that are used in data flow analysis for code generation and code optimization. It simplifies it a lot. So if a variable only has one definition, it has essentially one place where it's defined. It's never defined any other place. However, it can be accessed many times on the right-hand side. So what static single assignment form does is if I have a L value is equal to R value, you can use the same variable. Let's say you have A1. I can use it multiple times on the R value, but A1 can only happen once in the L value. Anytime I can always create a new variable called A2 and then start using A2. These two are not equal. Cannot have A1 again on the left-hand side of the assignment. So that's why it's called static single assignment form. And in fact, it's used in LLVM, used in most modern intermediate representations because it has so many nice properties when it comes to data flow analysis and also optimization. It's actually much simpler when each variable only has one definition because a variable has n uses and m definitions, right? So you can have, if you can redefine it multiple times, you can, it takes n times m different defined use chains if I'm allowed to redefine things. But if I have n uses and essentially one definition for each variable, then I always have a linear combination of the two. The worst case complexity is the same for static single assignment, but in practice, on average, it usually only has a linear number of definitions so that you can easily keep track of where something was defined and where something was used. We'll see later that static single assignment also simplifies register allocation because you're not redefining things. It makes it a lot easier to say, okay, this value is stale, let's move it to memory and keep the registers for what's going to be used in the inner loop, essentially. So we'll see that later about register allocation and why static single assignment helps. But what is static single assignment? It's very straightforward. Like we said, you can have the values of A that were used multiple times. Those can be done as many times as you want. You can use the value as many times as you want, but you cannot have the value of A being redefined over and over again in SSA form. So in SSA form, we assign it to A1 for the first line instead of just A. And then I can use A1 just like I used it over here. When I want to reassign it, value of Y plus, it's become B1 now instead of B. But now I assign it to a new variable A2. Notice that this A is used here, so this A2 is used here. I assign the addition to a new location A3. So if I used A again further down, I will be using A3, potentially use A3 or A2 or A1, depending on how the control flow works out. So static single assignment, you can only have the value of a variable on the left-hand side once in the program. So it's defined once, used multiple times. So for these straightforward cases, it seems quite easy to define static single assignment form. The complications arise when we deal with conditional branching, any kind of control flow. So let's take this example. I have a value of B, which I'm getting from an array. I have assigned a value of 0 to A. And notice that I'm using the value of A here, but I'm redefining the value of A. It's clearly not in static single assignment form. So how can we fix this? Well, we can call this first one A1. A1 can be assigned to 0. And here A2 can be assigned the value of B. But when it comes to using this A, should I use A1 or A2? So the answer is it depends. If it's coming from this entry point from basic block 3 into basic block 4, then of course it should be using A2. However, if it's taking this branch, if it's going from basic block 2 to 4, then A1 is the right answer because A1 is going to be the value you should use if it's coming from 2 because 2 takes the value of A from basic block 1. We want to encode somehow that the branching here matters. So which entry point you take into a basic block matters. And so what we do is we use something called a phi function. It can choose for you between A1 and A2, tell you based on the branch coming in, whether to choose A1 or A2, like we saw just now. So in this case, we have this phi function deciding between A2 and A1. So A2 is going to be the first one, the first arrow coming in. So I had switched them around, but this is the right way to do it. Is you would take the first one, the first argument comes from block 3, so it's A2. The second one coming here is A1. And the reason is taking this A1, which the value for A1 goes from 1. It's not destroyed in any way in basic block 2, so it's preserved for going into basic block 4. So in this case, we have a way of using a static single assignment, but when you have a conditional branch, you use this phi function in order to decide based on which path you're taking, what value you can use from the two previous sort of statically assigned values, A1 and A2. Notice that it's called A1 and A2, etc. So you know that in the original program, there was a single variable A. So we're going to add these subscripts essentially to tell you that in the underlying program, these were used in the program as a single variable A, but in static single assignment, they get split up into these multiple variables. There's a variant of SSA form called edge split SSA form, and the idea here is 3 has a predecessor of 2, 4 has a predecessor of 2 as well. The predecessor of 4 is 3, and at the same time I have the predecessor of 4 is 2. So if you look at 4, it has one parent, and its parent 2 is also a parent for 4. So we don't want to share this parent relationship between 2, 3, and 4. We introduce a dummy basic block called 5. It doesn't have any instructions in it. But now if you look at the predecessors of 4, it's 3 and 5. The predecessors of 3 is 2 and 5 is 2. The parent of 4, which is 3, having a parent which is 2, 2 and 4 now are not directly related. This is called the edge split SSA form. So this is a brief intro into SSA form. I think enough for you to understand what a phi function is. And that's sort of the main thing that you need to understand. For most cases, LLVM produces the phi functions for you, and we'll cover what that algorithm is in a future video lecture. You only really need to know how to construct these phi functions for yourself when you're doing the short circuit implementation in homework 4. In the future video lectures, we'll go into more in-depth into SSA form and how to build it automatically, just like LLVM does, so that you don't have to manually build all these phi functions in your code.